Hi, it's Ken Coulson here. It's really great to be with you for this 2023 Bible Science Conference. My name is Ken Coulson, and a little bit about myself. I graduated from Loma Linda University with a PhD in Earth Science, and my dissertation was on something called Stromatolites, which you're actually going to get to see a lot of today. I was living in the US for about 12 years. I'm presently living in Australia with my wife and kids. We were living in the US, as I said, for 12 years. And I was teaching at San Diego Christian College as full-time faculty, teaching physical science and earth science. Since then, I am now adjunct with San Diego Christian College. I'm also adjunct teaching for the Masters University as well as for Liberty University over in Virginia. So this presentation is about the Great Unconformity. Essentially, it's about the origin of the Great Unconformity. Now, I'm sure that the Great Unconformity is very, very well known to most of you being creationists. But for those of you who are not familiar with what the Great Unconformity is, it is a surface of erosion that does appear on most of the continents around the world. This is actually a cross-section through a section of North America, Western North America, going from Arizona. So you can see this black line in the map here of Western United States. The black line goes from Arizona over to California, and this is a cross-section through that black line showing you the Great Unconformity, which here is represented by this blue line. And you can see that the Great Unconformity cuts through, not only does it cut through sort of metamorphic and igneous rocks, it also cuts through sedimentary rocks. Now, this is highly exaggerated in the vertical direction, so just keep that in mind. Now, the issue is that most creationists out there, they believe that the Great Unconformity was produced when the flood basically flooded the land. It eroded out a lot of the land and left the Great Unconformity behind. And this is very, very common thinking in almost all creationist circles. So consider this quote here from one of my geology students. He says, "We would then find in the layers above the Great Unconformity a sequence of Cambrian rocks, sandstone, shale, and limestone. A sequence like this is known as a transgressive sequence, and it represents the transgression of the ocean onto continents." And then he says, this would be proof of Noah's flood. And this is very, very common with my students, and it's very, very common in the creationist community. The Great Unconformity is evidence, primary piece of evidence number one for the flood of Noah, and you can go anywhere in the world and see it. Now, you're probably asking yourself, well, if that's what most creationists think, then what is this guy doing rethinking the origin of the Great Unconformity? And the reason is because of these things, stromatolites. So as I said, this is what I did my research on. Stromatolites, you can think of them sort of as sort of columnar mounds made up of limestone mud. And the mud accretes in the sticky EPS sheets of photosynthetic cyanobacteria. So these cyanobacteria, they essentially populate the surface of the ground, and mud, lime mud, sort of coming down out of the water column, gets stuck in the EPS sheath. And then when the light gets blocked out, well, the community of cyanobacteria have to move to the next level. And the same process happens again. And each time that happens, it builds a millimeter or micrometer scale lamination. And as that continues to happen in an upward direction, eventually you will build a mound-like structure like what you're looking at here on the screen. Now this is actually a picture of the, it's a stratigraphic column of my research site in Western Utah where I did my research. And I did my research on these stromatolites right here that are found in the top of the Helen Maria member of the Notch Peak Formation. So this is the Notch Peak Formation from here all the way down to here. And these are three members that appear in the Notch Peak Formation. All of these sediments are Upper Cambrian sediments. And what's important is that these Upper Cambrian sediments represent sediments that most creationists believe were deposited in the flood, and they occur above the Great Unconformity. So maybe you can start to see the problem. How do you get all of these different growth structures, which are stromatolites, appearing in rocks that appear above the Great Unconformity in sediments that creationists have always thought were actually flood rocks. So to give you an idea of the scale of how many of these there are, consider this small section, which is 150 meters thick, 154 meters, so it's about 450 feet thick. And I've gone ahead and expanded it to the right. And what you can see here is the darker color represents actually stromatolitic material, or stromatolites, and the lighter color represents waxstone beds that are intercalated between the stromatolites. So essentially what you've got going on is you've got some stromatolites, for example, growing down here on bed number 1. And then there's an influx of a lot of sediment which causes them to stop growing. And then after that influx sort of slows down a lot, then you have a hiatus where these stromatolites can begin to grow again, hence you've got bed 2. And this sort of continues on up the geologic column. And so in this small section here, there are actually 11 different beds, and we're going to be looking at this bed right at the top here in particular. And the reason that I'm going to take you to that bed is because a lot of the material on top, a lot of the sediment, the dirt, has actually been eroded away and moved away, which means we can really look at these stromatolites in great detail. So let's go ahead and do that a little bit more. This, by the way, is where the research site was. It's in western Utah, where that blue star is. Oh, and this research, by the way, has generated 4 different papers. So the top 2 papers are in the secular literature. So there's the Polias paper on the left, and there's the Faces paper on the right. You can go to my website, creationunfolding.com, and you can that'll take you to the links. Unfortunately, still have to pay for the papers. However, the 2 bottom ones are creationist papers, and they're free. You can go to the link and you'll be able to download those PDFs straight away. The one on the left is the International Conference on Creationism, where I presented in 2018, and the one on the right is an Answers Research Journal. It's from 2021. It's the most recent, and so if you really want to kind of get in depth on this subject, then that would be the one that I would go to. All right, so let's have a look at that bed. So as I said, we're looking at this bed right at the top here. And this photo that you're looking at here, this is an amazing photograph of these stromatolites in 3D. So here what's happened is the sort of the dirt or the material that's around these stromatolites has sort of weathered out, and it's exposed the stromatolites in 3 dimensions. In fact, when you look at the photo, it's almost as though you're looking at these things in growth position. That's how amazing this is. So here, for example, is one of these columnar stromatolites. You can see it has that bulbous top on it. It's kind of rounded at the top. These stromatolites, so there's one there, there's one there, there's one there, for example, and there's 1, 2, 3, 4, 5, 6, I can see 7 in that picture. The stromatolites, remember, are made of sort of a limestone, macritic limestone material, but there's also this stuff in between. So between these stromatolites, this is called interspace material, and it's full of bioclastic hash. So it's got a ton of trilobite carapaces and shell material and things like that. It's very different than the material that actually makes up the stromatolites. And that bioclastic hash, it's indicative of a near shore environment, which is going to something that I'm going to be used in order to put forward the hypothesis that I will. Now, we were able, because these things had weathered out, we were actually able to pull 2 of these stromatolites out and take them back to the lab in Los Angeles, Eastern LA, in Loma Linda, and we're able to cut them in half. And so that's what you're looking at here. This is actually one of these stromatolites that we took back, and we were actually able to cut it in half right down to the very base of the substrate. So what you're looking at here is the actual place where it originally grew from. This is actually the substrate. Now these things were heavy, about 150 pounds each, but it was well worth it. We were able to get a good look inside these stromatolites. Now this is the same bed, it's that top bed, and what you're looking at here, this is this big picture with A on it, is a drone image. So here you've got a drone hovering over the surface of the bed, and as you can see, there is no material blocking our vision. We can see the top of the bed quite clearly. And I want you to see all of these little circles in the top of this bed. This image lower right here is actually a close-up image of the bigger image. And you can see those round to oblong circles. Well, they're stromatolites. And this surface has been eroded flat at some point in the past, so much so that it's literally cut the tops off of the stromatolites. So these ones, this picture at the top right here, that's when they're in 3D. That's another part of the bed where you can actually see the whole stromatolite in 3D. Yet in this part of the bed, the whole bed was planed flat, and now you're looking at a sort of a transverse cut through the top of these stromatolites. But what I want you to see here is that there are literally hundreds of these stromatolites in that photo that you're looking at. What's important about that is I was able to correlate this bed over about 8 square kilometers. Sorry, over 20 square kilometers. That's a fair distance. And so these stromatolites are literally cram-packed next to each other. You can see here the stromatolite and sort of an interspace material around them. They're like that over 20 square kilometers. So there are thousands of these things. But more than that, my colleagues, Art Chadwick and Leonard Brand, they actually had done some prior research before I started my research on these, and they'd actually correlated either that bed or a close correlation of that bed over an area of 2,600 square kilometers. And that's the area that I've got represented here by the triangle. Now, on top of that, secular scientists have also correlated these stromatolites, not the same bed, but all of those stromatolites in that section over an area extending from Western California right through Nevada from Eastern California on all the way over to into Western Utah. That's a huge area. And so now we're talking literally about millions and millions of these stromatolites sitting in many, many different layers, one stacked atop of the other. And on top of that, we actually find them all over North America. So the yellow dot here, that actually represents my research site. And the red dots and stars, well, that represents all the other locations around US and Canada where we find these stromatolites. So there's actually quite a few places, and oftentimes there are hundreds of them in these places, and they're on multiple different layers, just like my original research site. Now, what's interesting about this is that all of these stromatolites, you can sort of see they're on an arc. So you can see this is Newfoundland, this one over here, top right, and these stromatolites kind of go down into sort of New York area, down through Tennessee, across over into Texas, over into the area that I just showed you where there's lots and lots of them. That's California, Nevada, and Utah, on through Idaho, up into Alberta, Northwest Territories. And so you've got this kind of an arc of these stromatolites. And what's interesting is these stromatolites are sitting on what used to be the ancient shoreline of the continent of Laurentia. So that's what this black line is. This black line represents the Laurentian shoreline. And isn't it interesting that we find a lot of these stromatolites actually right on the margin of that Laurentian continent, which would make sense because these are near shore features. They grow in shallow water. And in fact, when a geologist finds stromatolites, it's really good evidence that they're near the shore. And so these are really good indicators for ancient shorelines. Now, on top of that, you've got the blue color. The blue color represents all of the different Cambrian sandstones that extend out from the Tepete sandstone in the Grand Canyon. So when people talk about the Great Unconformity, they'll typically take you to the Grand Canyon. And you've got the Great Unconformity, and then right above it, you've got the Tepete sandstone, which is the Cambrian sandstone. And as I said, almost all creationists believe that that Cambrian sandstone and all the layers above it represent flood deposits. Well, the blue color here represents all the different sandstones that are connected to the Tepete sandstone. Now, they all have different names, but they're all of roughly about the same age, which are Cambrian deposits. Now, notice that most of the stromatolites are actually sitting above those Cambrian deposits, and therefore are sitting above the great unconformity. And we actually find these stromatolites not just in North America, but we actually find them in many other places in the world. So that brings me to a point here where I want to dispel a common myth in modern creationism. And the myth goes something like this. There are lots and lots of stromatolites in the Precambrian. The Precambrian, according to most creationists, represents either creation week or pre-flood environments. And Cambrian on represents the flood. So most creationists are okay with having lots and lots of stromatolites in the Precambrian because, well, that's either creation week or it's the flood. But when you get into the flood deposits, they don't like having stromatolites there. And so there's a common myth out there that there are no stromatolites in the Cambrian, and that's just wrong. And there's another myth that's very similar to that, which says something like there are just a few stromatolites. In fact, just a tiny few, nowhere near as many as in the Precambrian. Well, that's false. I want to dispel that myth right now. This paper here was published by secular authors, Peters et al., but Shannon Peters is the same guy who wrote a paper with Gaines. I forget the guy's first name, but Peters and Gaines wrote a paper a few years ago on the origin of the great unconformity from a secular perspective. These guys are not Christians or creationists. And this paper was picked up by creationists all over the world because here you have these secular authors who are recognizing that, you know what, the great unconformity is a real thing. So you have not just creationists recognizing this unconformity exists in the world, but also secularists as well. But notice what he says in this paper. This is a quote from this paper. He says, stromatolites continue to exhibit large changes in prevalence after the evolution of metazoans. Now, what he means by that is metazoans appear in the Cambrian. Metazoans are just complex life forms, trilobites, shelled organisms, vertebrates, things like that. And of course, if you're familiar with the creationist worldview, you know that for the most part, they just sort of start in the Cambrian. And so what he's saying is that the stromatolites continued in prevalence after the Cambrian, and he even says that they transiently achieved Proterozoic-like prevalence during the Paleozoic. The Paleozoic is the same era that you find the Cambrian period in. So the Cambrian period's at the bottom of the Paleozoic era. What he's saying is that there are just as many stromatolites in the Precambrian as there are in the Cambrian. So, or just as many stromatolites in the Cambrian as there are in the Precambrian. He says transiently because they sort of really peter out after the Ordovician. You don't find many of them at all. But in the Cambrian and in the Ordovician, there are just as many as you find in the Precambrian. So let's as creationists, let's get rid of and dispel this myth that there are no stromatolites in the Cambrian deposits. Okay, well that of course presents a problem, right, as I suggested. How do you get millions of these stromatolites, which are essentially, when they come together, they're essentially solid reefs. How do you get these growth structures on multiple different horizons in sediments that are interpreted by creationists as being the very bottom or very beginning of the flood, right above the great unconformity? And the growth rate solution is one of the favorites. So we do have modern stromatolites today. Shark Bay, Western Australia is one place where they grow. There are other places as well. They're not really common, and they're not really a good analog. They're the best we have, though. And using modern stromatolite growth rates, maybe we can use that as a proxy for these ancient forms. So it turns out that modern ones grow at 0.5 to about 36 centimeters a year, or 0.2 to about 14 inches a year. Let's just call it 12 inches or a foot, just to kind of round things off and keep it simple. So let's say we can get 1 foot of growth per year. Well, if we take the section that I just did my research on, so we're looking at the right-hand map, we're looking at this 154 meter section, And to the right of that, I've expanded it, and we've got all that waxstone material. Well, look, if we pull the waxstone material out, and then just take all the stromatolitic material and sort of collapse it together, we end up with 50 meters thick of just stromatolitic material. So this is just biogenic material that's grown 50 meters thick or 150 feet thick. So if we look at the modern growth rate at 1 foot a year, then obviously if it's 150 feet thick, it would take 150 years to grow just this amount of stromatolitic material. Now, if we multiply that by 10, so an order of magnitude, well, then we could grow 150 feet thick of stromatolitic material in just 15 years, right? So 15 years, and if we could, if we multiply it by an order of magnitude, so that would be, we go from 1 foot to 10 feet a year, and then 10 divided into 150, well, that would give us 15 years. So that's one order of magnitude. 10 times that which they grow at today would still take 15 years. If we go up to 2 orders of magnitude, so 100 times the maximum current growth rate, then it would still take 1.5 years to grow this 150 foot thick section. And the problem is that I'm not even including this other section right above here in these other 2 members. There could be another 150 feet thick material there. And if you go to the left chart here, you're looking at now basically the whole geologic column, starting at the very, very base, starting at the Craton and going all the way through to the Upper Cambrian in Utah. Notice that this little bricks you see in this little geologic column here, that represents calcium carbonate. And there's 2.6 kilometers thickness of this calcium carbonate. And it's within that calcium carbonate that you find stromatolites. Now, the Notch Peak Formation, that's from the chart on the right, which is all of this, that is the Notch Peak Formation right there. This little box, that represents the Notch Peak Formation. And 2 of these little arch-looking things represent the stromatolites that are found in the Notch Peak Formation. Well, it turns out that there are stromatolites both above the Notch Peak Formation, okay, in the House Limestone, and below the Notch Peak Formation in the, I think it's the Ore Limestone or somewhere there. So there are stromatolites down there as well. And there are stromatolites above all of these in Ordovician sediments as well. So we've got huge thicknesses of stromatolitic material, and even if you increase the growth rate by 2 orders of magnitude or 100 times, it still is a long way from helping. And so this is a real problem. Now, the problem is increased by looking at erosion. Let me explain what I mean. So here, for example, is this red bar, very thin red bar, represents the top of the Cambrian. That represents, the 2 kilometers or so thickness of rocks that contain the stromatolites that we've been looking at. Now, most creationists believe that the flood started in the Cambrian and goes all the way through at least to the end of the Cretaceous, so all of the rocks in this section would be included. But there are other creationists that even would take the flood right up to sort of the bottom of the Quaternary here. That's a lot of rocks to get deposited in just 1 year, which means that in reality we've got to get all those stromatolites deposited at the very beginning of the flood, so literally in just a few weeks. So I think hopefully you can see why that solution, it's not going to fly. But it does get even worse than that. And this is where the erosion comes in. You see, there is a hypothesis out there in creationist circles about 100-foot tsunamis, thousands of them, that were hitting the continent during the flood, essentially eroding out more than 1 kilometer of bedrock right off the whole continent. And you can see that in this image, these massive tsunamis, thousands of them, that are sort of cavitating and eroding the continents flat. Here's the problem. At the same time that, and I've heard someone say 38,000 tsunamis are 100-foot high or 200 feet high tsunamis are cavitating the continent. At the same time as that, because it's early in the flood, these stromatolites are growing all over the world. You just can't have the two things together. Either you've got a kilometer of material being eroded during the beginning of the flood, or you've got these stromatolites growing. Can't have the two things together. Now, I personally don't think that the tsunami model is correct, at least for North America. There's no way you can have these stromatolites growing during when thousands of tsunamis are cavitating out the craton. And there are other problems as well. So, for example, if I go back to this slide, the stromatolites appear right here. These are all stromatolites. They appear in this section, this is 2.6 kilometers thick. So I'm looking at the left-hand map, and these little bricks represent calcium carbonate. This is sandstone down here. And this calcium carbonate is 2.6 kilometers thick, and it's really pure. I did something called insoluble residue tests on the material, the limestone from my site. That's where you take calcium carbonate, you put it in acid, and you sort of let it fizz away until there's nothing left. Or all that's left is siliceous material, stuff that doesn't degrade in acid. So things like mud and silt and sand. And you can find out by doing that how much sand is in your sample. And the reason that scientists do that is because by finding out how much sand is in there, you can find out roughly how far away that location was from the edge of the continent. As you get closer to the continent, your limestone gets filled with more and more quartz, more and more sand, and that's how you figure out how far away you are from the coast. Anyway, in my samples, there was about 3% quartz, or 3% sand, silt, and clay. Well, here's the problem. And then remember, this is all happening, okay? This is all happening right here at the bottom of what most creationists think of flood rocks. And now this is several kilometers thick, but compared to all of the rocks in the geologic column that were laid down in the flood, it's only a slither of all of those rocks. So as these thousands of tsunamis are eroding out the surface, they're taking sand and silt and clay and throwing it up into the water column. Well, how in the world is it that the limestone sediments got deposited without capturing a ton of siliceous material? Essentially, if that was actually happening, we shouldn't find any limestone. There should be nothing but sandstone. But we find pure limestones, which mean there were no huge 200-foot high tsunamis cavitating out and demolishing the cratonic rock down to little tiny pieces of sand, silt, and clay. It wasn't happening. The science just clearly says that that is not the case. So lots and lots of problems with the growth rate solution. And you know, I just added this extra part about erosion on there as well, just to really fortify that. So the next solution then is what's called the allochthonous solution. In other words, okay, so and this is despite what I just said about the tsunamis. Okay, if you think that the tsunamis are a real thing, then we still have to find out how in the world you get all these thick limestones, very, very pure in nature, without getting any sand hardly locked up in them. So the allochthonous solution says, well, the stromatolites, were they moved? Were they moved into this location? And the answer is no, and I'll show you why. So here is one of the stromatolites that I pulled, of course, from my research site. This one here, A. B is actually a cross-section of A, and you can see the black line where we cut it. What's really cool about this is that the top part's the stromatolite. The bottom part here, kind of the chunky part, that's actually the substrate, and you can see it better in B. You see how it has grainstone? This stuff's all bioclastic hash. It's like I said, it's like trilobite carapaces, bits and pieces of trilobites and shells, and brachiopods, and echinoderms, and all that kind of stuff that you find typically in Cambrian sediments. So what's interesting is when we cut it in half, we were actually able to find the place upon which the stromatolites started to grow. So that's what this arrow is pointing to. Now, another important feature of these stromatolites is that they grow in laminations that are always concave up. So the laminations are always a concave up curve like this. I've gone ahead and outlined a couple. There's this kind of wonky looking one in the bottom. But then this one that I've got at the base of the stromatolite, you can actually see that's what these laminations look like. They were always concave down, and that's how you knew the stromatolite was actually in a vertical position, because it was concave down. That's the way that the cyanobacteria grow as they move up through the mound. So clearly, this stromatolite did not get moved, it grew in place. Here's another one. So here you've got this is the grainstone, this is the actual substrate where it says grainstone. This is, we're looking at C now, and cast your eye upon this little triangular piece that's poking up from the bedrock. That is what the cyanobacteria got hold of, and in fact, if you have a close look, you can actually see the concave down laminations in this stromatolite that's starting to grow right on top of this elevated portion of the substrate, and that's because cyanobacteria like elevated areas. They like to attach to that. Now there's another stromatolite over here, and this in between it is grainstone material. That's kind of that interspace bioclastic material. What's really cool about this photo is you can't see it very well, but both of these stromatolites kind of grew up and then they grew into each other. And you ended up with sort of what's called a stratiform stromatolite right up the top, with all of this wavy sort of material. Now in D, there's another really clear example where the stromatolite is attached to the substrate. So this substrate here is actually ooids. Ooids are, again, calcium carbonate material. Basically, think of bioclastic material that's rolled around so much that's really nice and smooth, kind of like nicely smoothed out sand grains, but it's not sand, it's limestone. Or calcium carbonate, and that's the substrate. The substrate's made of these ooids, and this stromatolite you can see is clearly growing on the substrate. The stromatolite has not been moved into that location, it grew there. And here in E, the same thing. You can see this one, here's a nice elevated piece of grainstone. This is the substrate, and here you can actually see the nice concave down layers where the stromatolite is growing up. And here's some grainstone material that will separate that stromatolite on the left from the one on the right. Again, you've got in F here, you've got some stratiform stromatolites. So here, when you look at this, here where it says strom number 1, you can actually see it's growing again on another elevated area. So this dark area is the substrate. This is the stromatolite, and it's actually growing over that kind of elevated peak. But it's growing over it, not in a column. You can see it's actually growing here, and it actually goes right down like this. And this is what we call a stratiform stromatolite, where it's not growing in a column. It's actually growing kind of in a sort of in a sheet. And there are stromatolites in C as well that you can, in G that you can see as well. So lots of examples to clearly show that the allochthonous solution, it's not going to fly. These things actually grew in place. Now, to solidify that, here's actually a picture of some different stromatolite beds. You see, the top left, that's the bed we've just been looking at. But there are other beds. And interestingly, all of these stromatolites, they have different shapes. So the one on the right is a different shape to the one on the left. What's interesting about the one on the right is that the interspaces, that's the material between the stromatolites, is really narrow. Only about 1 or 2 centimeters. Really, really narrow. But here's what's interesting. If you have a look at this stromatolite, so the one the book is resting on, you can see that it has this little kind of a pointy section. Well, that's one stromatolite. Then this is another stromatolite. This is a stromatolite. This is a stromatolite. And that's the edge of a stromatolite because that's actually being broken away. But you've got 1, 2, 3, 4, 5 stromatolites in this picture that are outlined. How in the world did these 5 stromatolites, which were growing somewhere else, break up, get moved to this location, and get reattached in the same jigsaw puzzle pattern that they had where they came from? Obviously, that didn't happen. These actually must have grown in place. Same with the bottom left. You've got these kind of fat elongate ones. And so you've got 1, 2, and 3 that I've outlined. And then you can see this nice interspace material that's very consistent all around the forms, and that's true whenever you look around them. That interspace is always nice and consistent, which means these things weren't pushed up against each other because they'd been brought from somewhere else. It also means, again, these things are locking together like pieces in a jigsaw puzzle. There's no way that these three stromatolites that you can see here that are outlined were sort of growing somewhere else, and then they were ripped up, deposited here in the same puzzle-like pattern that they had where they were growing before. And the same with the picture on the right. So you've got some more elongate stromatolites here. So here's one here and here's one here. Now these ones are really special because they're actually about 20 centimeters long. They're about 15 feet long, so 5 meters long, about a couple of meters high. So what's that, 6 feet high. I want you to imagine basically like a big tall ship. And I want you to imagine that this structure is sliding across the ocean floor on a 20 centimeter wide base, along with thousands of others that don't fall over. And not only that, but when they stop, they park next to each other in such a nice way that all the interspaces, so you can look at the interspaces, are all nicely spaced. I don't think so. That's not the case. Now this one's actually interesting. The arrow is pointing to a joint between one stromatolite and the other, and that's because these cyanobacterial communities, although they're isolated in their stromatolites from a next door stromatolite, every now and again they'll cross over and build a bridge to another stromatolite, and that's what you're seeing in that picture. And of course, this of course means, what's the solution then? What are we going to do, and how are we going to explain all these data? Because you simply can't have millions of these stromatolites all over the world growing in this kind of a catastrophic flood. Well, basically, I propose, this is the original flood boundary. So look at the words Proterozoic and the words Archean there, and just think in terms, that's the Precambrian. Okay, so essentially in the Precambrian, we don't have metazoan fossils. Now, for those of you who are a little bit savvy, yes, we have the Ediacara biota. I suggest going to my paper where I get into that, but I don't want to get into that complexities here. Just for the sake of simplicity, think in terms of the Precambrian just being sort of single-celled life, algae, bacteria, things like that. It's not until you get to the Cambrian that you get these huge swaths of very complex creatures like trilobites and shelled organisms and echinoderms and all these kinds of organisms appear, invertebrates as well, in the Cambrian. Now, again, the traditional explanation is, well, that's because as the flood is eroding the Craton, right, that's the great unconformity, it's then dumping all of these creatures that were in the ocean onto the land, and that's why we have all of these fossils. And that's been sort of the staple in creationism. So now you have a two-prong piece of proof, if you like, that supposedly is able to point to Noah's flood. That is the surface of erosion, and now you've got all these animals. Well, I don't think you have to have it that way. In fact, if that was the case, and the flood was dumping all of these organisms onto the land, and that's what the Cambrian, all these fossils represent, then wouldn't we expect to find just a few shelled organisms or trilobites somewhere in the Precambrian? I mean, that got buried before the flood from some lakes or some rivers or some storms, just buried just a few to be fossilized. No, we don't find any in the Precambrian. You essentially have this stark contrast, essentially no complex life, complex life. I think the best way to interpret that is in terms of the curse and the onset of death. Before that, in the Precambrian, the reason there are no complex organisms there is because none of them died. Yet in the Cambrian, this record of all of these dead bodies, trilobites and bivalves and echinoderms and all of these organisms, all of these vertebrate fish as well, they died because that was the consequence of Adam's sin. So that's the stark contrast. I think that makes much better sense, which would mean then that the Cambrian deposits represent pre-flood environments that got buried at some stage later, not in the flood. And I think that's a really good explanation. That would mean then that we'd have to raise the pre-flood flood boundary somewhere into the post-Ordovician. Now, exactly where, I don't know. And the reason I don't know is because creationists have been so stuck on the Precambrian Cambrian boundary and the great unconformity being the onset of the flood that we haven't really wanted to think about putting a boundary anywhere else. But I think, as I've shown in this video and with this research, when you have millions and millions of these stromatolites, these growth structures all over the world in Cambrian and Ordovician deposits, then they simply cannot be growing in the global flood. Best to think of them in terms of the pre-flood world, and also best to think about that distinction, that contrast between the Precambrian and the Cambrian in terms of the curse and the onset of death. Okay, what do we do with the great unconformity? Well, I want you to think about this. What other geologic event can you think of that may have created a surface of erosion all over the world? Have a think about it. Is there another event that you can think of that might have done that? Now, if you're thinking about Creation Week, then I would agree with you. This is what it says here in Genesis 1:9-10. And God said, "Let the waters under the heavens be gathered together into one place, and let the dry land appear." And it was so. And God called the dry land earth, and the waters that were gathered together he called seas. And God saw that it was good. Look, you've got some incredible amount of geologic activity occurring right here during Creation Week. An astonishing amount of geologic activity. In fact, a lot more than what we would see going on with the flood of Noah. I think this is a great place to put the great unconformity. The great unconformity is a surface of erosion that's evidence for Creation Week, not the flood. Okay, so for, again, further resources, you can go to the secular journals that have been written. You can go to the creation ones. I think the Answers Research Journal on top, bottom right would be the best one to get the most information. I do have a YouTube channel, and on that YouTube channel, I've actually got 3 videos on this subject. You want to go to YouTube, punch in Creation Unfolding, go to my playlists, and then put in how much of the geologic record was deposited during Noah's flood. That's the playlist that you want to look for, and there's 3 videos in there that go into a lot more detail as well. So these are the resources that I used. It's been wonderful to be with you all. I hope you're enjoying the conference, and we'll talk to you again soon. Thank you. Goodbye.